All right, Advanced Placement Chemistry, Hoover High School. This is the instructional video on Unit 9, Kinetics, and in your textbook that covers chapter 14. So what is kinetics? Kinetics is the study of how fast a chemical reaction occurs. Similarly, kinetics can be used to see how far from reactants to products a reaction has proceeded in a particular amount of time. The proper term for how fast something happens is called rate. Rate is a change in a variable per unit time. So chemical kinetics is interested in two types of rates. One is the molar concentration, that is moles per liter per unit time. So often that's expressed as moles per liter for each second that goes by, molar per second. Also, it can be used for gases, in which it would express the change in pressure per unit time. So what is kinetics? So molarity, let's review what that is. It's the number of moles of the solute divided by the number of liters of solution. That's the solute and the solvent together. Molar concentration per unit time is molarity per time. So again, that's change in moles per liter over change in time. For example, how many moles per liter of a reactant are used up each minute? Or how many moles per liter of a product are produced each minute? And the brackets, the square brackets, are used to express molar concentration. So whenever you see those square brackets, it means moles per liter. The rate expression for reactant A, and A is just a hypothetical reactant of some sort. It could be CO2, it could be CH4, it could be whatever you want it to be. It's written as negative delta concentration of A over delta time. Delta is change in. So change in concentration over change in time. The negative sign indicates that the concentration of the reactant is being reduced. That is, the reactant is being used up. So the rate expression for a product, B, again a hypothetical product of some sort, is written change in concentration of B for every change in unit of time. And this expression is positive because products are being produced. So this is called a particulate diagram. It just shows a proportional representation of reactants and products. A particulate diagram uses symbols for reactants and products. The symbols are shown in proportion to the number of moles in the reaction. So this is simply giving you an illustration of two reactions that proceed at different amounts of time. So both of these reactions start off with a certain amount of reactants, and we assume there's no products present at the beginning of either of these reactions. So for the first reaction, A plus B equals C, the reactants are the red circles and the blue ovals, and as that proceeds, by 45 minutes you have only what are purple ellipses, and those represent the products. So you start off with all reactants A and B, and you end up with all products C. And it may have taken less than 45 minutes, but by the time 45 minutes has elapsed, you have all products. In the second reaction, you start off with reactants D and E, that would be the blue circles and the yellow ovals. And as you move across to 45 minutes, you have some green ellipses, and those represent the products. However, you'll notice you still have blue circles and yellow ovals. So one of two things has happened. Either this reaction is slower than the first reaction, or it could simply be that it's reached an equilibrium, and that's a concept we'll get in after this unit on kinetics. That is, it does not actually react all the way to products, but that you end up with some products and some reactants at the end of the reaction. But in either case, it's saying what this is really trying to illustrate is that the first reaction moved faster than the second reaction. Okay, so this is a graph, shows the concentration of reactants and products from the beginning of a reaction until 30 seconds. So at the beginning, everything is a reactant. That would be the black curve, and you can see it has a concentration of 0.4 molar. and that's at the beginning. There's no products at the beginning of the reaction. That's not always true. You can have reactions which do start off with some of the products already in the vessel or the container, but in this case they're saying that there aren't any. At the beginning, everything is a reactant, black line, and there are no products, red line. As the reaction proceeds for 30 seconds, most of the reactants turn to products. The steeper the line, the faster the concentration is changing. So in other words, as a unit of time, as you go from 0 to 5 seconds, and on the black line, on the reactants line, a lot of the reactants are used up. You go from 0.4 down to 0.3. If you come out farther, though, between 25 and 30 seconds, you'll notice that as that 5-second interval goes by, you don't go down nearly as much. That means you're not using up nearly as much of the reactants. And that's typical of a reaction. At the very beginning, when you have a lot of reactants, they're used up faster. As you start to run out of reactants, the reaction runs slower. Same with the products. At first, the products are being made very quickly, between 0 and 5 seconds, and then as you get toward the end, 25 to 30 seconds, you still have some products being made, but not as quickly. Just keep in mind that how steep the line is an indication of how fast the reaction is taking place. And it could be steep in the positive direction, such as the red line, or it could be steep in the negative direction, such as the black line. But the steepness of the line, either positive or negative, doesn't matter, will indicate how fast the reaction is taking place. So the reactant line is the steepest at the beginning when the concentration is greatest. The negative slope means the concentration of reactants is decreasing. The product line is increasing rapidly at the beginning when the reaction is fastest. All right, so there you see, using the red triangles, that you can see each horizontal part of the triangle, that is the left to right part, are the same length. They represent the same amount of time. But you can see as the reaction proceeds, the vertical part, the up and down part of the triangle, gets shorter and shorter as you go from left to right. And that's because for each amount of time that goes by, less and less of the reactant is being used up. The reaction is slowing down simply because there's not as much reactant there to produce the reaction. So the rate speed is lowest where the slope is less steep. Okay, and then this diagram illustrates that kinetics also applies to gases. Instead of molar concentrations, you can see that the measure is in terms of gas pressure, and that's placed on the vertical axis. The gas pressure could be measured in any one of the units of measure we use for gas pressure. This one is torr. It could be atmospheres, it could be pascals or kilopascals. All right, so assume that a reaction takes 1 minute to complete. In 1 minute, that means that 2 moles of per liter of substance A, that's the reactant, are used, and 1 mole per liter of A2 is produced. So you can think of that as 2 hydrogen atoms combining to become a hydrogen molecule. The rate expression for each of these would be written as negative change in concentration of 2A per minute. Now you notice the double negative sign. Since the reactant is decreasing in value, then there's a negative 2A inside the concentration. The reason for the negative sign outside is that since a rate cannot be a negative number, a rate is a speed of something, and speed can't be a negative number, it's got to be a positive number, you must put the negative sign on the outside to turn the rate into a positive number. On the right-hand side, it's saying that the change in the concentration of A2 being produced, that's a product, that's going to be increasing per 1 minute. So the rate of using up 2 moles of A has to equal the rate of producing 1 mole of A2. In other words, both of those things have to happen in the same amount of time. You have to use up 2 moles of A for every 1 mole of A2 that you produce, and all that has to take place in the same amount of time, in this case 1 minute. So these expressions indicate the rate, how fast at which these two processes take place. The negative sign in the negative 2A indicates that the molar concentration of A is decreasing. It is normally not written. The negative sign in front of the expression, the one on the outside, indicates that the rate must be a positive number. So the double negative signs make this rate positive. So to relate how much of a product is made when a certain amount of reactant is consumed, the two expressions must be equated. In other words, both of those things have to happen in the same amount of time. Well, since the reactant is being used up twice as much of the reactant is being used up for the amount of product that's produced. In other words, 2 moles of A is being used up for every 1 mole of A2 produced. If you want to equate the two, then you have to multiply the 2A by 1/2. So that equates the two. And that's called a rate expression. So to relate how much of a product is made when a certain amount of reactant is consumed, the two expressions must be equated. Since twice as much A is being used as A2 being produced, the negative 1/2 term must be placed in front of the reactant side to equate the two sides. Normally, decreasing the reactant 2A does not show the negative sign inside the brackets since it is known to be decreasing. Generally, to write a rate expression for any reaction, the reciprocal, that is, you flip the coefficient of the coefficient, is placed in front of the molar rate of change for each reactant and product. All of the reactants and products can be equated in the following way. So if you have A moles, let's just say that number is 3 of substance A, then in the rate expression you would write 1 over A, or 1 over 3 in my example, times the change in concentration of A over change in time. Similarly, the small b in the second reactant, you would flip that over and make it negative 1 over b. Again, both the reactants are decreasing in concentration. They're going down, so it's a negative sign. Now you go over to the products, and remember, all of these 4 things that you see have to be happening in the same amount of time. So you flip the C number, whatever that coefficient, the small c is, you flip that over, it becomes 1 over small c. And that's a positive because that's a product. It's being produced. It's increasing in value. And finally, the 1 over the d becomes small d becomes 1 over small d, and that's times the concentration in big D for concentration in time. So that's how you equate all of the products and reactants. Simply take their coefficients, flip it, make the reciprocal, and if it's on the reactant side, you have to put a negative sign in front. Okay, so here's an example of some actual chemicals. So take the reaction BrO3 plus 5Br plus 6H gives you 3Br2 plus 3H2O. And now the question is saying, assume that the value of negative BrO3 per time, so that's the rate and has a negative sign in front of it because it's a reactant, is equal to 1.5 times 10 to the minus 2 molar per second. Again, that's moles per liter per second at a particular time. So the first question is, or the first statement is, write the complete rate expression. So you simply take all of those coefficients. So in front of BrO3, there's no coefficient. That means it's a 1. So it's negative 1 over 1 times the concentration of BrO over delta T. Should be BrO3 actually down there at the bottom. And then the 5Br, you flip that, it's negative 1/5 change in Br over change in time. And then the hydrogen, same thing, flip the 6, make it 1/6. Those are all negatives because they're on the reactant side. Now you go across the arrow to the product side and you have positive 1/3 times the change in Br2. And then you have 1/3, positive 1/3 times it. That should be a change in concentration of H2O over there on the right hand side. And this is just showing each of those as I just stated them. Okay, so assume that the value of the reactant BrO3 is changing at a rate of negative 1.5 times 10 to the minus 2 molar per second at a particular time. Determine the rate of formation of H2O, which is on the product side. So what you can do is take those two, the part of the rate expression that just includes those two, the reactant BrO3 and the product H2O. So you just equate those two, you just pull those off from the previous slide, and you have that. And now we know that the change in negative BrO3 over time is negative 1.5 times 10 to the minus 2. So we can just substitute negative 1.5 times 10 to the minus 2 in where you see the red rectangle there. And when you substitute that in, then you get the negative negates itself. There's double negative, so it becomes positive. Again, a rate has to be a positive number, and that equals 1/3 of the H2O, of the rate of the H2O. And so you simply do a simple algebra, multiply both sides by 3, and you end up with the change in concentration of water, H2O, for change in time is 4.5 times 10 to the minus 2. So it allows you to see how much of one of the products or reactants will change with respect to a change in another one of the products or reactants, and that's what this rate expression does. Okay, now the rate law, that's really kind of the centerpiece of kinetics, and it's the main equation used in kinetics. So take the following reaction. So again, the small letters represent coefficients, numbers like 2, 3, 4, whatever. And the A, B, C, D, the capital, represent some sort of reactants or products like CO2 or CH4 or NH3 or something else. So a rate law has the following form. The rate of the reaction, that is how fast the reaction is taking place, equals K times the concentration of reactant A raised to the X power times the concentration of reactant B raised to the Y power. So the thing to notice first of all here is that the only things that go into the rate of reaction from that chemical equation are the reactants. The products do not go into that. There should be an arrow, by the way, in between the chemical reaction up there. So only reactants are used in a rate law for kinetics. So bracket A is the molar concentration of reactant A. Bracket B is the molar concentration of reactant B. K is the rate constant, and that's a function of temperature. Remember when you put your glow sticks in the cold water and in the hot water, the reaction ran faster. They got brighter. That meant the reaction was running faster in the warm water. You didn't have any more reactants in the glow sticks. You didn't increase the number of reactants. What you did is you increased the temperature, and therefore you increased that rate constant K by putting the glow sticks in the warm water. The exponents X and Y are determined by experiment. You cannot simply take the coefficients small a, small b, and put them up there. They are not the same as the coefficients. So you have to do that by an experiment, and we're going to show you how to do that using experimental data. Okay, so the order of a reactant is the exponent X or Y on the reactants. So A1 is read A, concentration of A, if it has an exponent of 1, you usually don't write the 1, but if it does, then that's read the reaction is first order in A. If the concentration B has an exponent of 2, then that's read the reaction is second order in B. So order number is simply what the exponent is. The order of a reaction is the sum of the orders of the reactants. So the reaction, for example, rate equals K, A concentration of A raised to the first power, concentration of B raised to the second power, is a third order reaction. Again, you just simply add the exponents, and that will tell you the order of the reaction. Okay, take the rate law and give a relationship between the rate K concentration A squared and B. The rate law gives the relationship between the rate and speed of the reaction. And 1, the concentration of A in molarity, so moles per liter. 2, the concentration of B. And 3, the rate constant, which is a function of temperature. Generally, higher temperature produces faster reaction rate, just like the glow sticks. So those are the 3 things that affect how fast a reaction takes place. The concentration of the reactants and the value of K, which is determined by the temperature at which the reaction is taking place. So this is a summary how different order reactants affect reactions. If A to the 0, if a reaction is 0 order, then the concentration does not affect the rate of the reaction. In other words, A to the 0 simply equals 1. So it doesn't matter what concentration you put in for A, it's always going to be 1. Therefore, you're saying that the concentration of A doesn't affect how fast the reaction takes place. A to the first, if a reaction is first order, then doubling the concentration doubles the rate of the reaction. Tripling the concentration would triple the rate of the reaction, and so on. So it's a direct relationship between the concentration and how fast the reaction takes place. A squared, if a reaction is second order, then doubling the concentration quadruples the rate of the reaction. So if, for example, you had 1 molar initially and you square that, you get a rate of 1. But if you double the molarity from 1 to 2, then it's 2 molar, then 2 squared is 4. So by doubling the concentration from 1 to 2, you quadrupled the rate of the reaction. It went from 1 all the way up to 4. So how is the rate of the following reaction affected by changes in the concentration of A and B? So the answer is you just invent some numbers like I just did for each variable. Just the exponents are fixed, and don't worry about units of measure. So let's make all the variables equal to 1. So K equals 1, molar concentration of A is 1, molar concentration of B is 1. So everything's a 1, so the rate turns out to be 1. If you double the concentration of A, then that 1 goes to a 2 for the A. Now you square that, it becomes a 4. So you've quadrupled the rate of the reaction by doubling the concentration of a second order reactant. And finally, if you double the concentration of B, that's raised to the first power. So doubling the concentration of B doubles the rate of the reaction. So conclusions for this example. Make all variables equal to 1 in the initial reaction. Then double the concentration of A, and so on. So this is going over that same point. So here's an example of how to write a rate law from experimental data. So nitric oxide gas, NO, reacts with chlorine gas according to the equation NO plus 1/2 mole of Cl2 gives you NOCl. The following initial rates of reaction have been measured for the given reagent, which is another way of saying reactant concentrations. Now again, these numbers come from an experiment. So you're given these assuming that you conducted or someone else conducted an experiment to get these data. You cannot get them from the chemical reaction. They are data that came from laboratory experiments. So what they're saying here is in the lab you ran a reaction, and you ran the reaction with 0.25 molar, this is reaction number 1, 0.25 molar of NO and 1.5 molar of Cl2. And the reaction ran at a rate of 1.19 molar per hour. So again, it's measured in molarity per unit time. In this case, the time is an hour. In reaction 2, you had a concentration of 0.5 molar, so of NO. So you had twice as big a concentration of NO. The concentration of Cl2 stayed the same, 1.5 molar. And when you did that, you found that the reaction ran at a rate of 4.79 molar per hour. And then you ran an experiment a third time. And this time you used 0.5 molar of NO and 3 molar of Cl2. So you doubled the concentration of Cl2. And when you did that, you found that the reaction ran at a rate of 9.59 molar per hour. So now we're going to use that data to compute the rate law for this particular reaction. So to create a rate law in the form of rate equals K, concentration NO raised to the X power, Cl2 raised to the Y power. So note the coefficients in front of the reactants, such as 1/2 in front of Cl2, play no part in this process. So don't let that confuse you. So first, find the value of X, the exponent for NO, by isolating the change in concentration of NO and the change in rate that it produces. So what that means is you want to find two of the reactions where Cl2 does not change. The only thing you want to be changing is the concentration of NO and the rate. So if you look at the three equations, you see that reactions number 1 and 2, the Cl concentration, the Cl2 concentration does not change. It stays at 1.5. And the NO concentration doubles from 0.25 to 0.5. And then the rate of the reaction goes up from 1.19 to 4.79. So you create a ratio of the concentrations of NO. And you usually want to put the bigger number on top. So 0.5 over 0.25. That way you don't end up with a decimal number. And that equals 2. Now you want to do the same thing with the rates, and you got to do them in the same order. So if you, in this case, you put reaction 2 on top and you put reaction 1 on the bottom. So for the rates, you're going to do the same thing. Reaction 2's rate, 4.79, goes on top, and reaction 1's rate, 1.19, goes on the bottom. And when you divide those, you may not get exactly 4, but you get something close to 4. So now what you do is you just set up a little equation here. And this just states that since the ratio equation 2 over 1 in the first ratio, it must be equation 2 over 1 in the second ratio. So now equate the concentrations and rates with the exponent x. So the concentration doubled, and so that's 2. You raise that to some unknown power x, and that will give you the increase in the rate of the reactions, and that number's 4. So 2 raised to the x equals 4, and x equals 2. So there you solved for the exponent x. So the equation so far is rate equals K, concentration of NO squared, that's the number you just calculated, concentration of Cl2 to the y power. So the reaction is second order in NO. Now we're going to do the same thing for Cl. So we look for two reactions where NO doesn't change, and that would be reactions 2 and 3. So we want only Cl to change, and we want to see how the rate will change with a change in the concentration of Cl holding NO constant, so it doesn't change. So those are the two reactions we choose. So we create a ratio of the concentrations of Cl. So we put equation 3 over equation 2. That's 3 over 1.5. Again, we get the number 2. We create a ratio of the rates. So that's going to be 9.59 over 4.79. That approximately equals 2. Again, we did equation 3 over 2 in both cases. And now we equate the concentration of the rate. So we take the number that we got for the concentrations, which was 2. We raise that to the y power, and that's going to equal the ratio we got for the rates, which was also 2. So 2 to the y power equals 2. Therefore, y equals 1. The equation so far is rate equals K, concentration NO squared, concentration Cl2 to the first power. So we've solved for both of the exponents. Now the only thing we have to solve for this equation is the value of the rate constant K. So how do you do that? Well, we have the following reaction so far. Didn't write the exponent 1 above Cl2, but it's implied there. Now we need to find the rate constant. We do this by choosing one of the reactions. You can pick any one of the reactions you want. In fact, if you want to try out all three of them, you should find that they should give you the same value of K. And then substituting the concentrations and rate. So we're going to choose reaction 1. So this would make the rate equation look like this. So the 1.19 is substituted for the word rate, equals K, that's what we're trying to find. And now we put in the actual concentration of NO, 0.25 squared, and now we put in the actual concentration of Cl2, 1.5, and so you have one equation and one unknown, K, and you just do some basic algebra, and you'll come out with K equals 12.7. So the rate equation for this particular reaction is rate equals 12.7 times the concentration of NO2 squared times the concentration of Cl2. That means you can pick any concentrations you want of NO and Cl2 and put them into that equation, and it will tell you how fast that reaction would run, what the rate of that reaction would be. Okay, now we're going to get into a little more sophisticated view of the rate law. And in order to do this, we need to understand a little bit about logarithms. We talked about this in class, so we'll go ahead and do that. Okay, so logarithms are a way to express large and small numbers that increase exponentially. For example, the Richter scale measures magnitude of earthquakes. So some sample measures, for example, are 100, which is 10 to the second power, 100,000, which is 10 to the fifth power. So you can see that 100,000 earthquake would be 1,000 times more powerful than a 100 earthquake. Or 100 million, that's 10 to the eighth power. It's not possible to plot numbers from 100 to 100 million on a normal piece of paper. It is, however, possible to plot the log of these numbers. So the log of 100 is 2, the log of 100,000 is 5, the log of 100 million is 8. It's simply, what a log is what number do you have to raise 10 to get 100? You have to raise it to the second power. What number do you have to raise 10 to get 100,000? You have to raise it to the fifth power. That's what a log is saying. It's saying what is the exponent of 10 that will get you to 100 or 100,000 or 100 million. So we can plot the logs, 2, 5, and 8. Those are very small, manageable numbers. So logs can also create straight lines from particular curves, and that's the reason natural logs are used in chemical kinetics. So you don't need to understand logs or natural logs in detail. Don't let this scare you. You just have to know how to plug in the numbers to the equations when needed. So you only need to understand how they're used in kinetics and how to apply formulas with natural logs. In this unit, you will use the natural log function lnx, which is simply log, log, to the base e power, and e is a special number called Euler's number, 2.71. You don't need to understand any of that. You just need to recognize them in a formula and know how to punch the right button on your calculator. So trust me, you don't have to be an expert at natural logs. So in this unit, we'll use the natural log function lnx to create straight line graphs out of reaction rate curves. A natural log is a log to the base e power, so log e to the x equals ln x. You don't need to have an in-depth understanding of ln and e. It will be enough to know when it applies to kinetics. Okay, this is not a course in natural logarithms, but you need to understand the idea of an inverse operation for natural logs. So an inverse math operation reverses another math operation. So for example, addition is the inverse of subtraction. So if I start with some variable y and add 2 to it and then subtract 2 from it, it gets me back to y. In other words, the subtraction undoes the addition. They reverse each other. If I start with y, so starting with y, adding and then subtracting 2 returns to y. In math, there's a special number called Euler's number, E, which is equals 2.718. This number describes changes that appear in nature, such as chemical reactions. So you will use the following inverse operation between E and the natural log ln. ln x is the inverse of e to the x. And so you're going to need to use that relationship to solve some of the problems. So you will use the following inverse operation. ln x is the inverse of e to the x. So take any number y. And if you take y and then you raise e to the y power, and then you take the natural log of that, it gets you back to y again. If you take the natural log of y and then take whatever you get from that and raise that to the e power, you get you back to y again. So in other words, e and ln reverse each other. They're inverses. So in both cases, you begin with y and you end up with y. So e to the y and ln of y reverse each other. Another principle of logs you should be familiar with is the following, that the log of a times b equals the log of a plus the log of b. And of course, these principles apply to natural logs as well. It's any logs. These principles would apply to any logs. The log of a divided by b equals the log of a minus the log of b. There's a number of other principles that apply to logs, but you don't need to know them for this particular unit. And all we're doing is focusing on what do you need to know to do the chemistry. Up until now, we've been writing rate law as rate equals K times concentration of A. It could be also with a concentration of other things, B, C, whatever. This is a rate law of a first order reaction. You notice that time is not a part of this equation. So this equation is for a specific moment in time. Now, we are going to introduce a rate law that tells us how concentration changes with time. And this is called the integrated rate law. And for a first order reaction, this law is natural log of the concentration of A minus natural log of the initial concentration of A equals negative rate constant times time. So A is the concentration of reactant A at a particular time. A0 is the initial concentration. That means the concentration at the beginning of the reaction. And T is the time that we were interested in knowing what the concentration of A is. In other words, how far into the reaction we are when we get to a certain concentration of A. So the integrated rate law says the difference between the natural log of a beginning concentration and the natural log of a final concentration is equal to the negative of the rate constant, K, multiplied by time. So the basic rate law, K times concentration of A, tells us how fast the reaction is going at a very specific time. The rate law, the integrated rate law, natural log of A minus natural log of the initial concentration of A equals negative KT, tells us how the concentration changes between two times. So a good analogy for this is that it's like the difference between saying that a car is traveling at 30 miles per hour at a specific moment in time when you look at the speedometer, that would be the basic rate law, and saying that it took the car 1 hour to travel from Oceanside to Chula Vista. So you're getting a difference in two times and a difference in two locations in the integrated rate law. It's not simply how fast is it going at a specific moment in time. So a first order reaction rate curve can be converted into a straight line using the following equation. You don't need to understand the math involved, just understand that this is a valid way to turn the variables into a straight line. So if you take the integrated rate law we just showed you and you rearrange it by adding natural log of A0 to both sides, you end up with natural log of A equals negative K times T time plus the natural log of the initial concentration of A. So the graph on the left shows the actual decrease of a reactant in a first order reaction plotted against time. So it's the same curve we've seen before. It goes faster at the beginning, the concentration drops fastest at the beginning when there's a lot of reactant, and then as you start to use up the reactant, the A, it gets slower and slower, and so the line gets less steep, the curve gets less steep. Now the graph on the right shows the natural log, that's ln, of the concentration plotted against time. So instead of A, concentration of A against time, it's the natural log of A plotted against time. So look at the axes on the two graphs and see how they differ. This graph forms a straight line where the slope is the negative of the rate constant K. So now what you see is one of the advantages of why we use natural logs, because it turns that curve on the left into a straight line. And it's much easier to work with straight lines, and we know that that straight line has a slope that is the negative of the rate constant. So if we can make that plot, then we know what our rate constant is for this equation. So the equation is in the form of a straight line. So ln A equals negative kt plus ln A naught. And that's in the form of an equation you've seen for a straight line, y equals mx plus b. So m is the slope, that's the negative k. X is the independent variable, that's on the x-axis of the graph, that's the time. And the y-axis of the graph is the natural log of A. And the y-intercept would be the natural log of the initial concentration. If we put in a value for time t, we will find a natural log of A. However, we're interested in A, not in natural log of A, right? We get natural log of A, that's great, but we want to know what the concentration of A is. We don't want to know what the natural log of the concentration of A is. So this is where we use the inverse operation. If we do come up with a value ln of A for an answer, and we have some number for that, then what we do is we simply say we raise e to that power. So e to the ln A will give us the concentration of A. So that's how we get rid of the natural log. We just raise it to the e power, and then that gives us back A. It's an inverse. Also, the slope m of the line is negative k, which is the rate constant. Actually, k is the rate constant. So an integrated rate law incorporates time into the equation. The rate law we have been working with so far does not have a time variable. That's the one we were working with up until now. So the rate law we have been using tells us how fast the reaction is proceeding at a specific point. For example, what is the rate of the reaction at this point where the arrow is pointing? On the right side, the integrated rate law using time tells us how long it will take for the reaction to go from some beginning concentration, A0, to some final concentration, A. For example, from A0 to A as shown with those two arrows. So it gives us two different points in time and two different concentrations of reactant. So this shows a concentration versus time of a first order reaction. This is the curve we are used to seeing for the concentration of A that is being consumed. And on the right, this shows the natural log of the concentration versus time. So again, look at the axes and be sure you're clear on the difference between the x-axis is the same, the time axis is the same, but the vertical axis, the up and down axis, is different. This graph shows us to see the first order reaction as a straight line, allows us to see the first order reaction as a straight line and determine the rate constant K. So here's a problem, and this is a problem that's going to take 4 slides. It looks a little complicated. Some of the parts of this are easy. This is something you might see on an AP exam, and 2 of the parts are pretty easy if you know what you're doing, if you just know the basics of this subject. The other 2 might take a little bit of effort. Okay, so here's the question. The question is in blue, and it's going to appear on the next 4 slides. The decomposition of SO2-Cl2 produces SO2 and Cl2. So that's called a decomposition reaction. You have a single reactant that's breaking into 2 products. At a certain temperature, the concentration of SO2-Cl2 was monitored as a function of time. A plot of the natural log of SO2-Cl2 versus time produced a linear straight line. So right away that tells you it's a first order reaction. If a plot of the natural log of the reactant versus time gives you a straight line, a negatively sloping straight line, then it must be a first order reaction. That's one of the characteristics that they might ask you about on the AP exam. It's a linear straight line plot with a slope-intercept equation given as follows. So you have y equals negative 0.000310x minus 2.14. Now notice that slope is going to be the negative of the rate constant. The negative 2.14 is not really important. It just happens to be what the initial concentration was for this reaction, but that doesn't affect what the value of K is going to be. So you could substitute that 2.14 in for pretty much any other initial concentration. So the first question is, what is the order of the reaction? And the answer is, it's simply the slope of that line, the negative of the slope. So, excuse me, I'm sorry, I jumped ahead. So what is the order of the reaction? Well, again, if it's a straight line, if the natural log of SO2Cl2, the reactant, versus time produces a straight line, then it's got to be a first order reaction. So, first order reaction. Read the question carefully. The information says that a plot of natural log SO2Cl2 versus time produces a straight line with the equation shown. This is a negative sloping equation. We do not need to know the specific numbers to answer this. So the key point is, if a plot of a natural log of concentration versus time produces a straight line, then the reaction is first order. The second question, what is the rate constant? Well, there it is. It's the slope of that line. It's the negative of the slope of that line. The slope of that line is minus 0.000310. So if you take off the negative sign, that's the rate constant. A rate constant is always a positive number. Okay. So the slope m is the negative of the rate constant. Therefore, the rate constant is 0.000310. Note, rate constant k are always positive. The third question. At the same temperature, 0.2 molar of SO2Cl2 is decomposed. Remember, a decomposition reaction is where a single reactant breaks up into two products. What is the concentration of SO2Cl2 that remains after 5 minutes? Well, since the rate constant is expressed in seconds, you have to convert minutes to seconds. And there's 300 seconds in 5 minutes. So the answer is, first you want to identify what your variables are, what you're given to work with. So the temperature must stay the same or the rate constant will change. So you notice in the question up at the very top in blue, it says at a certain temperature. So they're just clarifying that the temperature is not changing. Generally in a kinetics problem, if they don't say that, you will assume that. So SO2Cl2 initial is 0.2. So that's going to take the place of that 2.14 in the equation. Again, you could have started with any initial concentration and ended up with the same K value and everything else. It doesn't matter what concentration you started off with at the beginning. So this is the initial concentration of SO2Cl2. We have our time, 300 seconds. So we plug it into the equation. Okay, and so that gives us ln of SO2Cl2 equals negative 0.00310 times 300 seconds plus the natural log of 0.2. So now we can solve for the natural log of SO2Cl2. And this is a continuation of the same question. There it is right in the middle of the page. And now if you crunch the numbers on that, you get that the natural log of SO2Cl2 is negative 1.702. So now what we need to do is we don't want to know the natural log of SO2Cl2. We want to know what the concentration of SO2Cl2 is. So what we do is use our inverse operation. So we raise both sides, take to the e power, or rather you raise e to each of those sides. So in other words, any math operation that you do to one side, you do it to the other. So we take the natural log of SO2Cl2, we make that the exponent of e, and on the other side we take negative 1.702 and we make that the exponent of e. And by doing that, we inverse the e and the log, so we end up with the concentration of SO2Cl2. We got rid of that natural log sign. And if you do the same operation over on the right side, e raised to the negative 1.702, that's just a calculator operation, you get 0.18 molar. So what that means is, after 3 seconds, we started off with 0.2 molar, and 5 minutes later, or 300 seconds later, we ended up with 0.18 molar. And the final question in this sequence is, what is the concentration of SO2 and Cl2 at this time? So answer. We assume that we started the reaction with no SO2 or Cl2. This is a fair assumption in chemistry problems when we are not given an initial concentration of products. So we assume that SO2 and Cl2 were 0. So we look at the balanced reaction that we started with for these, and we notice that there's 1 mole of everything in this reaction. There's 1 mole of SO2Cl2, there's 1 mole of SO2, and there's 1 mole of Cl2. So think about what this means. It means for every mole of the reactant SO2Cl2 that we use up, we gain a mole of SO2 and we gain a mole of Cl2. It's a straight 1-to-1-to-1 relationship. If we use up 2 moles of reactant SO2Cl2, then we will gain 2 moles of SO2 and we will gain 2 moles of the other product Cl2. So whatever SO2's number is in a decrease, whatever SO2Cl2's number is of moles in a decrease, and decreasing as a reactant, the same number of moles of the 2 products each will go up. Okay, so the initial concentration of SO2Cl2 was 0.2 molar. The final concentration of SO2Cl2 was 0.18. If we subtract the final from the initial, we get 0.2 minus 0.18 equals 0.02 molar. So that means we used up 0.02 molar of SO2Cl2. Okay, so the equation tells us that 1 molar of SO2 and 1 molar of Cl2 was produced for every 1 molar of SO2Cl2 used up or reacted, or 0.02 molar. So everything is 0.02 SO2Cl2 was used, and 0.02 SO2 was produced, and 0.02 Cl2 was produced. So 0.02 molar of SO2 and 0.02 molar of Cl2 was produced in 5 minutes. Okay, half-life. So the half-life of a first-order reaction. Half-life is the amount of time it takes half of the concentration of a reactant to be consumed. A first-order reaction is that no matter what concentration of the reactant is present, the time it takes for half of it to be consumed is always the same. So, assume that each time interval in this graph is 1 minute. Then each minute, half of the concentration of the reactant at that time will be consumed. So the key, this is only true for first order reactions, not for zero and not for second order reactions, this relationship. So that half of whatever is remaining of the reactant is going to be consumed in the same amount of time. So for all other reactions, the amount of time it takes to consume half of the reactant depends on the concentration. There's a simple formula to determine the amount of time of one half-life, and it's only true for a first-order reaction. And that is the time 1/2, that's the half-life, equals 0.693 divided by the rate constant. So here's an example. A reactant has a concentration of 8 molar and a half-life of 1 minute. What will be the concentration of the reactant after 3 minutes? Answer. A half-life of 1 minute means that the existing concentration will be reduced by half for each minute that passes. There will be 1 molar remaining after 3 minutes. So we start at time 0, we have a concentration of 8 molar. 1 minute later, we have half of 8, which is 4. 1 minute after that, from minute number 1 to minute number 2, we cut the concentration in half again. So it goes from 4 down to 2. And then in the third minute, from minute number 2 to minute number 3, it goes half again, and that's from 2 down to 1. So example, what is the half-life of a first-order reaction with a rate constant of K equals 2.3 times 10 to the negative third? There's a simple formula to determine this. That's the formula given on the previous page. So we have the rate constant, so we simply take the number 0.693 divide it by that rate constant, and in this case we'll get a half-life of 301 seconds. Okay, so that wraps up this first instructional video. There's a second one on the way for kinetics. This will get you through the assignment that was given to you on Monday. It's due on Thursday. I postponed the deadline. But get on this. If you have questions, come in for tutoring, and I'll be happy to help you with that. And I'll put a solutions video up for that assignment as well. Okay, we'll see you on the next video.